Okay, I forgot to record. Okay, so just have some review, and it is generated by semi-norms, which is given by we write it as a compact subset K, and with some order M, which is the supremum of all x over K, and uh, the sum of all alpha with order not greater than M, all the alpha derivative of f. I think it is also like this at the value x with value at x. Okay. We say it's generated by semi-norms means that open sets are of the form that is x, where the set of all functions g such that uh, all these norms of g are not greater than delta. So we say a space of functions is generated by some semi-norms means that the open sets are something of are generated by these open subsets, and then we just say the dual of this, and we write it as d prime u, the space of distributions. This is our general setting of distribution, or we say it is a generalized function, because it is not necessarily a function. It is just a linear map, and it can have no. So the fx, f at a point x can make no sense. So we say it is a generalized function. It is not really a function. And we know that the classical space of functions are subspaces of these distributions, and we endow it with the weak star topology. That is generated by elements in CC infinity U, and we know that this is locally convex, and the dual of U is the space of all is the space of test functions. And we know that LPU for any U for any P, and also the local LP and the space of all I think the spaces of all case order differentiable functions are all subspaces of D prime U. This is because for any such F, in one of these spaces, we can just write F as a linear functional as the integration over U and F times phi dx. So this gives us the inclusion of these classical function spaces into D prime U and also CKU, which we also require the supremum of all these to be finite. But the most interesting space is the Sobolev space. I think we have used this concept of Sobolev space many times before we introduce what is really a Sobolev space. This is associated with the norm with a positive integer k and also a positive real number p, which is the sum of all alpha not greater than k, and the integration over u of all derivatives of order up to p and dx with the exponential and with the exponent 1 over p. So this is somewhat like LP norm with k order derivatives involved. And we know that this is the Sobolev norm. And the Sobolev space WKPU is the completion of the space of all compact. No, it should not be the space of. It should not be a completion of this. It should be a completion of like LP. So it's a subset. Okay, it's a subset of d prime u, or we say it should be a function. So it is a subset of L1u, such that the Sobolev norm is finite. And we readily know that there is a natural inclusion by d prime du, and which is just the space of more compact just for smooth functions with compact support, and kpu to lpu and w minus 1 pu to wkpu minus kpu to the space of distribution. Here we say the Sobolev space with negative integer as exponent is just the dual of wkp. It is a dual of w1p. So we mean the dual because yes, the dual is known with respect to the topology of WKPU to make it a banana space, and we know this is a banana space. But it is with respect to the topology on D prime U, so that it is a subspace of the space of distribution. And also we have the Holder space, which is the space of fractional differential or fractionally differentiable functions. So we require f is continuous and f is holder of order alpha if we have the norm alpha, f alpha, and alpha should be greater than 0 and less than 1. No, it should be greater than 0 and less than 1. So it is just given by the supremum over all x and y in U with x do not equal to y, and x minus y of order alpha, and with the numerator, the sum of the difference of fx and fy, and this should be finite. And we write C alpha U to be the space of holder Holder continuous functions of order alpha. And in fact, we can let alpha to be any positive integer, to be any positive real number. So C alpha U is just a set of F such that F is belongs to CK, and any derivative of F, any derivative of F of order K is holder of order alpha minus K. So we have introduced the order integrand for us to state the following overlap embedding theorem. Ingredient. This will be fatal in our further discussion, so I have to state it. Let U be a subset of Rn with Lipschitz boundary conditions. You can ignore this condition because any manifold, I think, yes, can always be achieved. It can always be achieved on smooth manifolds, so you can ignore this. And K a positive integer, and also P greater than 1, but and it can achieve to infinity a positive real number. Then we will have the following. The first one is the case when Kp is greater than n. In this case, we have WKPU can be embedded into the space of all holder continuous functions of order alpha, where alpha is greater than or equal to 0 and bounded by the real number Kp minus 1 quotient by P, and we can achieve alpha equals P Kp minus n over P once this is an integer. This is not an integer. The second case is when Kp is less than n. But then we cannot expect that the space of a superlap space can embed into the space of continuous functions, but it can embed into LQ function on U for P for Q greater than or equal to P and bounded by n minus P over n minus Kp over np. And the third is that if Kp is equal to n, then we know that WKPU will embed into LQU for all Q greater than P. So this means that NP quotient by n minus Kp is equal to infinity. So the second and the third conditions are almost the same. And also the corresponding result, there is another corresponding result called Rayleigh conjectural theorem, which states the compactness. For compactness, we must have some more regular, more strict inequalities. That is UKP just as above. We assume that U is bounded. UKP as above, then For Kp greater than n, we will have the embedding into C alpha of Q is compact for all for alpha strictly less than K minus P over N. And the second is that if Kp is less than N, then we will have the Sobolev space embed into LQ. I think we can say it is less than or equal to for LQU is compact for Q greater than P, but strictly bounded by the real number n minus Kp over Np over n minus Kp. So these two embedding result is essential in our proof of the Fredholm theory and also the elliptic estimate. So I will not say the proof here because it is very long. It is a long exposition and with many inequalities. So if you want to know the proof of this, you can find it in Evans or Adams Sobolev spaces or other standard materials. Okay. So our main topic is the elliptic estimate. For Cauchy-Riemann operators. And here we are treating with non-smooth Cauchy-Riemann operators, but we can firstly consider the case of smooth Cauchy-Riemann operators. And I will follow my thesis paper. So it is in the, I think, let me see what the, so yes, 14 in seminar web page. So the elliptic estimate just we consider the local estimate because with the local estimate we can then easily glue it together to get a global estimate. So we first let's consider the local coordinate UZ, where U is a subset of H, possibly with boundary. And Z a local coordinate. And the Cauchy-Riemann operator D on the local coordinate UZ with the standard D bar plus A, where A is a complex smooth matrix valued differential form. But in local coordinates, we can just identify E with the trivial bundle Cn. Yes, Cn. So we can just that A is a matrix, and we can drop the differential one form because it is not a one form. It is actually a 0-1 form. So any 0-1 form can be represented of the form Aij dz bar, and we can just drop the dz bar to write it as Aij, so it is just a matrix. And we can also drop the d bar d bar should be from omega 0 to omega 0, 1, but we can then identify omega 0, 1 with omega 0. So it can just be a set of vector value. Can be just viewed as a operator, differential operator between vector valued uh, vector value functions. So any section can be viewed as just a function from U to R twin or to Cn. So we have the following. Let U be a smooth function on U with value in R of 2n and satisfies the boundary condition, maps the real line into the standard totally real subbundle. Then there exists a complex sub, open subset of U and a positive constant. C such that the 1p norm of U on the subset V is bounded by the d bar of U of the LP norm on U plus the LP norm of U on U. So this is our main result in this section, because with this at hand, we know that once we know A is a complex and smooth matrix value function, then we will have d bar plus A times U of the LP norm. It is bounded by d bar of U the LP norm plus AU of the LP norm. But we know that A is just a smooth operator, and it belongs to L infinity because sigma is compact. So it is also bounded on the set U. So we have this is bounded by the L infinity norm of A times the LP norm of U. So the L infinity norm of A can be added into the positive constant C. So we will get a similar estimate for the complex smooth matrix value difference for the complex smooth consumer operator D. And notice that the fact that A is complex linear makes no use in this group, so we can also assume that it is a real linear. That means that this means that this is the same type of estimate holds for any real linear and smooth Cauchy-Riemann operator D. So we can just replace D bar by D. But the proof is very no, I don't think it's very difficult. It is somewhat difficult because we are treating with LP estimates. Here we must assume that P is greater than 1. So in order to do this, because U is smooth, we can just set that F be d bar of U, and then we know that df is equal to d bar of U, and we know that d bar of U in real coordinate is just an Laplacian of U. So in order to treat with the operator d bar, we can instead treating with the operator Laplacian. Then we just replace here the U by no, we cannot replace. And if we can prove the following estimate, the W1P norm of U is bounded by the C times the Laplacian U LP. The LP norm of Laplacian of U plus the Laplace of the plus the LP norm of U. What I'm going to say. Yes, then it follows directly that the L1P W1P norm of U is bounded by the D bar of U, the LP norm of the D bar of U plus the LP norm of U. So we're just going to treat with the Laplacian operator. And in this case, since U satisfies the boundary condition, we can say that the Laplacian of as the Laplacian equation U should satisfy the okay, so let's first ignore the boundary conditions and consider the estimate for Laplacian. This is a very classical, this is a very classical theory of Calderon and Riemann. That is, since we want to develop the LP estimate for the Laplacian of U, and we know that the Laplacian of U is equal to the del. No. The estimate is not of this form. It is of the form. So we can just write it slightly more general as the Laplacian of U is equal to f plus ds of g plus dt of h. So we have three terms, one with two terms with some weaker derivatives in a weak sense. So it in a weak sense means in a distribution sense, that is for any test functions, they are equal. Okay, I forgot to state some more things. I forgot to state, yes. For distributions, we have also two types of actions. The first one is we can have derivatives of mu, where mu is a distribution, just by integration by parts. It is equal to -1 of the order of alpha and mu epsilon phi. Mu epsilon phi means the value of mu as phi. And also we have multiplication by smooth functions, where f is smooth, p is equal to, and in fact f can be f can be ck or can even be LP local. No, it depends on the distribution. So anyway, it is always true if f is infinity. Yeah. So we have two types of operations on the distribution. The first one is derivative, the second one is multiplication by smooth functions. So here we can say the Laplacian on. So we can say that the partial differential equation in a weak sense. And in this case, we will have the following estimate is the W1P norm of U is bounded by C times the LP norm of F plus the LP norm of G plus the LP norm of H plus the LP norm of U. then we are done because we know that uh, then we are done because we know that uh, I mean we know that yes, in our case f is 0, so it is only bounded by ds of g and dt of h, and uh, one point uh, yes, here we also assume that u, f, g, h are also LP local functions, so that they are functions that make sense on u. Then we have the full estimate, and so yes, this will imply uh, the previous proposition because we know that if we write c bar, if we write f equals to no uh, okay, so let's first try to prove this. The first is that when f, g, h are all zero, that is, then u is harmonic, and it follows by Wey's lemma that is if Laplacian u is harmonic in a weak sense for u in any locally integrable for u locally integrable, then it follows that u is smooth. So by Wey's lemma, u is smooth, and since u is smooth, then we readily have this estimate because of the uh, mean value inequality, mean value property. So this needs some computations, like we need to write u equals to the we must write u equals to the convolution of u with the mean value. The mean value kernel, like it is pi r square because it is in dimension 2, so pi r square, the integration over the form dxr and dy, and here we just make it into a function. So this equals to the step function at the characteristic function at the space B, X star, and Y. Yeah. So B0 are Y. And the convolution with this gives the same function. So we can compose again. And we know that the derivative of U, so the derivative of U for any I, we can just act it on the other on the other side, and we know that the convolution of full such chi R is differentiable. And in fact, it lies in C1. So this is in C1, so this is in C0, and we will obtain the PIU, the LP norm of this is not greater than equal to the LP norm of U. Well, V is slightly smaller, so we have the space for convolution. And this proves the case for U harmonic. And in general, we need another technique called Cardinal-Zygmunt inequality. In general, that is, the Laplacian of U is in the weak sense F plus DSG plus DTH. So let K be the fundamental solution of Laplacian operator. That is, Laplacian K is equal to delta in the weak sense. Then this gives us the fact that the Laplacian of K convolutes with U is equal to U itself in the weak sense. Here we must impose something like the convolution of between distributions, but I think it is clear. And in special cases, we can prove that the convolution makes sense. So we can then give the let V be the convolution of K of F plus convolution with DSG plus convolution with DTH. And we know that in local coordinates, K is equal to log of Z times a constant C for some C. And the derivative between convolutions can transform between convolutions, so it equals to K convolutes with F plus K1 convolutes with G plus K2 convolutes with H, and we times the beta, so that and we convolute with a cutoff function beta, so that they all have compact support. But the beta should be identically 1 on V, so that it does not affect the value on V. Then we have the Calderon-Zygmunt inequality, which is given by the gradient of K1. K1 and K2 means that partial order derivatives of like the dsk and this is dtk of K. So we have the convolution with LP norm on U is bounded by the convolution. is bounded by the positive constant c times the convolution times g itself, and but we know that beta has support on v, so it is equal to so it is bound, so it is equal to the yes, so it is equal to the norm of beta g at and c at over the support of beta, and then we have also the gradient of k2 convolutes with g beta g over the LP norm of u is bounded by beta h, yeah, h. The LP norm of h on u, and which is equal to the integration over the support of beta. Now we want to so yeah. So we also want to estimate the convolution of K with beta f, but this follows from Young's inequality. This means that yeah, no, it is not Young's inequality. It is Mikov. Anyway, so we have this the convolution of K1 with beta f and also K2 with beta f, and then we apply Young's inequality to see that we let to yes to give the estimate of that on the support of beta. That is, we just subtract K1 and K2 from the convolution, and the remaining part is beta f, and they are L1 bounded. So we so left with a positive constant c. Then with the free estimate, we will already obtain that the gradient of v at v is bounded by c times f of support of beta plus g plus h on the support of beta. But we know that beta is not greater than yeah, and we know that Poincare inequality, that is the gradient is always the main part of the Sobolev norm. That is the Sobolev norm of v is bounded by the gradient of v, the LP norm of the gradient of v, and it is bounded by f plus g plus h on the support of beta. And we know that v is just the convolution of k by the convolution of k with f, g, and h. So we have the Laplacian of v is just equal to, in the weak sense, f plus dsg plus cth, and which is equal to the Laplacian of u in the weak sense. This tells us that u is just v plus some harmonic function, some harmonic function So A. Then we know that the W1P norm of U is bounded by U minus the W1P norm of U minus V plus the W1P norm of V. And we know that V is bounded by C, the LP norm of S plus the LP norm of G plus the LP norm of H. And plus the harmonic, the W1P norm of the harmonic function. So we know the harmonic function is always bounded by the harmonic function, the LP norm of the harmonic function. Yeah, and this tells us that finally, because we can further estimate V, so we obtain that the W1P norm of U is bounded by C times the LP norm of S plus the LP norm of G plus the LP norm of H plus the LP norm of U. Okay, so we have proved this estimate, and it follows directly that the W1P norm of U must be is bounded by C times. It's also bounded by the Laplace d bar U, the LP norm of d bar U plus the LP norm of U. This is because since we know if we write F equals to d bar of U and with U smooth, then we know that the Laplacian of U is just equal to d of f, and which is ds f plus I times dtf. No, I think this is minus and with 2 over 1. So yes, and then we just apply the above estimate to obtain that the norm, the W1P norm of U on V is bounded by C times DSF, the LP norm of DSF plus the LP norm of DTF, and plus the LP norm of U on U. So the problem is how to transform the derivative of S into S. Uh, I think okay. So let's go with the same procedure. To, no, at least it follows that if d bar u is 0, then we know that d bar composed with d is again 0, and which is equal to the Laplacian of u, and this tells us that u is smooth. So in general, we have d bar u equals some f and f. Uh, how to say this? Okay. there is some problem with. Oh, okay, let's just move on. So the fatal question is why the Carlton-Simon inequality holds in this estimate. Uh, you can take it for granted. It is not so. It is rather technical. I think uh, I think it is not deserve. It does not deserve a rigorous proof. So for every t greater than 1, we have c greater than 0 and f smooth with compact support. In R2 or in Rn, then we have to estimate the gradient of Ki composed with f convolute with f. The LP norm of this is bounded by the LP norm of f on the larger set. So, and this is just a direct consequence of Carlton-Simon theory. That is, we must apply some Carlton-Simon. We must apply the so the proof is roughly that we first prove the L2 case. That is t equals to 2. It is true. Then if it is true, then the Caesar theory tells us that the convolution, the T, which maps F into a convolution of Ki with F, is weakly L1. And then we use interpolation to obtain LP for all P1 for all P greater than 1 but bounded by 2. And then we use dual operator to obtain the estimate for P greater than 2 and less than infinity. So this is a rough proof, but we need the Carlton-Simon theory. That is a very lengthy argument, and you can see in Barry-Simon if you actually want to know the proof, and also for my thesis. Okay, in Appendix C. Okay, and this is in Chapter 6. Let's just move on. So we have established the proof for the case when T is a real linear Cauchy-Riemann operator. It's a smooth real linear Cauchy-Riemann operator, and we can readily obtain the global estimate. That is okay. Oh, we still want to check the case with boundary because we are always treated with functions with boundary conditions, that is compact support or so. And with boundary conditions, we just let u be the double of u. That is, we just do an extension. If this is u, then we just make the region to be the union of u and its symmetry part. So this will give us the required region that we can do a estimate. And then on u, it is just it is just half of the estimate because from we can easily see from the construction of this double and the extension of f to tilde f over u tilde. And we also have v and v tilde. So the estimate is effective on the u tilde, then we can give the estimate on the original region u. So that is how we treat with the case with boundary. And now we give the global estimate, that is the integration over sigma is bounded by the integration of del bar u over LP sigma plus the integration of u on LP sigma. So we just glue them together. But here, note that we are treating with, note that this is not d bar, it is the Cauchy-Riemann operator d. But here we are treating with the Cauchy-Riemann operator d, and locally d is d bar plus c. So we need the du of the LP is equal to d bar plus a times u of the LP norm, and this is bounded by d bar u of the LP norm plus the AU of the LP norm, but this is bounded by the L infinity norm of A, so we obtain our result, that is the W1P is bounded also by du plus u. Okay. And since this is V and this is U, but sigma is compact, this tells us that it is okay to cover the whole sigma by finitely many Vi. Then we can have I equals 1 to L. We sum them together, we sum them up, and it is bounded by the sum of all these over U. But the LP, the whole, the integration over sigma is bounded by this, and the sum of this is bounded by a larger C times the integration over the whole LP, and this is a required result. This is how we glue the local pieces together to obtain global estimate. Because, in fact, any such global estimate can be reduced to local estimate. So it is, so the fatal, so the essential difficulty is on the local estimate, is on the Calderon-Zimmer inequality. And we can just take it for granted. And then we must treat with the case when A is not smooth. It is only when it is only of class WKP, and then we must apply the Sobolev embedding theorem in order to. So we must imply the Sobolev embedding theorem. Yes, and the companions in order to develop theory, develop the similar estimate. And no, we don't need the estimate, but we know that we need a similar Graham properties for non-smooth Cauchy-Riemann operators. Okay, so this is time is almost up. Are there any questions? If not, then we will end this talk and uh, see you tomorrow.